In today's lecture, we're going to talk about Galois theory. So we need to start with the basic definitions. Let K over F be a field extension. Then we start with the key definition from Galois theory. Okay, so to remind you of a definition we've already seen, an isomorphism sigma from the field K to itself is called an automorphism. And the set of automorphisms forms a group where the multiplication action is given by composition of functions. And we denote this group aut K. Okay, so let sigma in aut K be an automorphism. Then we say that some element x in K is fixed by sigma if sigma of x equals x. So we say some element x in K is fixed by the automorphism sigma if sigma takes x to itself. And then we define the group aut K over F, or the automorphisms of the field extension. We define this as the set of those automorphisms which fix every element in F. So we define this, and this set forms a subgroup of aut K. So we define aut K over F, or automorphisms of the field extension, as the subgroup of aut K consisting of those automorphisms which fix every element of F. So in symbols, aut K over F is defined to equal the set of all elements sigma in aut K such that sigma x equals x for all elements x in F. So it's the set of automorphisms which fix the ground field F. Okay, so then Galois theory is largely about the interaction between this group and the field extension. So Galois theory is largely about the interaction between the group or K over F and the field extension. So one of the goals of Galois theory is to let you study field extensions via group theory. So it lets one study field extensions via group theory. And in fact, it was actually Galois who invented group theory for the purpose of studying field extensions. Okay. Okay. So we start with a proposition to show you why the group of automorphisms of a field extension is relevant. So to start with, let K over F be a field extension. And choose some algebraic element over F. So let alpha in K be algebraic over F. So this means that there is some polynomial with coefficients in F such that alpha is a root of that polynomial. So let Fx be some polynomial with coefficients in F such that alpha is a root. So with f of alpha equals 0. Okay, the claim is then that for any automorphism of the field extension sigma applied to alpha is a root of f as well. So the conclusion of the proposition is that for any sigma in aut K over F, f of sigma applied to alpha equals 0. So in other words, the automorphism takes a root of the polynomial to another root of the polynomial. Okay, so this is very easy from the definitions. So let's write out our polynomial fx c0 plus c1x plus c2x squared plus cn xn, where the coefficients all lie in f. Okay, so we know that f of alpha equals 0, and we want to see what happens when we apply the automorphism to alpha. So f of sigma alpha equals c0 plus c1 sigma alpha plus c2 sigma alpha squared plus cn sigma alpha to the n. And now we use that sigma is a automorphism, and in particular a field isomorphism. So since it's a homomorphism, we can write these elements like so. So sigma alpha squared is the same as sigma applied to alpha squared, since it's a homomorphism. Okay, and now we use that sigma fixes the the field f, and in particular it fixes all of the coefficients of the polynomial. So I can write C naught is fixed by sigma. So I can write it as sigma applied to C naught, sigma C1, sigma alpha plus sigma C2, sigma alpha squared, sigma Cn, alpha n, and then using again that sigma is a group homomorphism. So I should say this step is because sigma fixes x, sigma fixes f, and then this is the same thing as sigma applied to C naught plus C1 alpha plus C2 alpha squared plus Cn alpha to the n, or the same thing as sigma applied to f of alpha, because this term in the brackets is just f of alpha. But we know that f of alpha is 0 since alpha is a root. So this is sigma applied to 0, which is 0, since sigma is a homomorphism. Okay, so this completes the proof. So what this previous proposition tells us is that any automorphism which fixes the ground field f has to permute the roots. It has to take any root of a polynomial to another root of the polynomial. Okay, so let's look at some examples. So to start with, let's consider the extension of Q given by the field generated by root 2. Okay, so if you like, then Q root 2 using the results proven in previous lectures. This is the same thing as Qx. So the minimal polynomial for the element root 2, which is a real number, the minimal polynomial is x squared minus 2. So Q adjoin root 2 is the same as Qx quotiented by the ideal x squared minus 2 using the results from the previous lecture. Okay. So now let tau be some element, be some automorphism of K which fixes Q. Okay, so x squared minus 2 is the minimal polynomial of root 2. And we know from the previous proposition that tau has to permute the roots of the minimal polynomial. So tau of root 2 well, this polynomial has roots plus or minus root 2, so tau of root 2 has to be plus or minus root 2. So further, we've seen for this field Qx modulo x squared minus 2 that this is a field extension of degree 2 equals the degree of the polynomial x squared minus 2 with basis given by taking powers of root 2. So the basis should be the 0th power, that's 1, and the first power, and then we stop since it has degree 2. So 1 root 2 is a basis for Q root 2 equals Qx modulo x squared minus 2 over Q. So we have that Q adjoin root 2 is the set A plus B root 2 for rationals A and B. Okay, so what we've proven now is that any automorphism which fixes Q of this field K equals Q adjoint root 2. It has to fix all rationals, and it has to take root 2 to plus or minus root 2. So tau A plus B root 2 equals A plus or minus B root 2 for A, B, and Q. This means that there are only two possibilities for the group of automorphisms of Q root 2 over Q. So there are two elements in Q root 2 in aut Q root 2 over Q. Namely, there's the identity, which is the case of choosing the positive sign, and there's an element sigma, which is what you get when you choose a negative sign. So sigma A plus B root 2 equals A minus B root 2. Okay, so in particular, notice that the automorphisms of the field extension are in this case a group with two elements. So we have two elements, meaning that there's only one group of two elements, just as the cyclic group of order 2, which is what this automorphism group must be. But just for now, notice that the automorphism group has two elements. The number of elements in the automorphism group of the field extension equals 2, which in this case is the same as the degree of the field extension. Okay. Okay, so let's look at another example. Let's now look at another extension of the rationals. Let's look at a cube root of 2, which is Qx modulo the ideal generated by the irreducible polynomial, irreducible by Eisenstein, x cubed minus 2. Okay, so you can check that the minimal polynomial x cubed minus 2 of a cube root of 2 has the following three roots. Which are two of which are complex numbers. So we have the cube root of 2. Then we have the cube root of 2 multiplied by minus 1 plus I root 3 over 2. And cube root of 2 times minus 1 minus I root 3 over 2. Okay, so you can check that these all give you cube roots. These give you all elements which cube to 2 in the complex numbers. But only one of them is real. So this is the only real root. The others have imaginary parts. Okay. So since only one of these is real, only the cube root of 2 lies in the field that you get by adjoining cube root of 2 to Q, because this has to be the smallest subfield containing Q and the cube root of 2, but since both of these elements are real, this is certainly a subfield of the reals. Okay, so now if tau is some automorphism of the field extension which fixes Q, then it has to take the cube root of 2 to another one of the roots of the minimal polynomial, first of all. And secondly, it has to, since it's an automorphism of a subfield of the reals, it has to take that element to another real number. So the only possibility, since we only have one real root, is that tau fixes the cube root of 2. Okay, so tau. But the other thing we know is that we know right, we know that we can write this this as the degree field 3 field extension qx modulo x cubed minus 2, and then this has the basis 1 cube root of 2 squared. So we go all the way up to 1 less than the degree of the minimal polynomial. Over Q. So any element in Q, cube root of 2, have the form alpha A plus B cube root of 2 plus C cube root of 2 squared. I shouldn't say equals here, I should say isomorphism. For A, B, C in Q. And then, well, tau has to fix everything because it has to fix all rationals, and we've proven that tau has to fix the cube root of 2. So tau A plus B cube root of 2 plus C cube root of 2 squared. Well, it has to fix A, has to fix B, it has to fix cube root of 2, so it has to be the identity. So in this case, there's just one element in the group of automorphisms of the field extensions. This group is the identity. And then it's a group with just one element. So the number of elements so I should say this this absolute value sign here, these two vertical lines, this means cardinality or number of elements, just to spell that out. So this is, when I'm looking at a finite group, this is the number of elements. Here in this case, we've proven it's just one. It's only one element, which in this case is less than the degree of the field extension, which is 3. Since the minimal polynomial has degree 3. Okay. am I doing for time? Okay, so let me just make one more remark about this. So notice that that if I want to get all three roots, so if I want to get all three of these roots into the same field, then it's not just enough to attach the real root to the rationals. I also have to attach this element I root 3, and then I'll be able to get all of the three roots into the same field. So notice that the smallest subfield of the complex numbers, which contains all the roots of the minimal polynomial, so containing all three roots of the minimal polynomial x cubed minus 2, is the field. So you have to adjoin the real root, the cube root of 2, and you should also adjoin I root 3, which is cube root of 2. Let's write this. Let's write I times cube root of 3 as cube root of minus 3. Okay, so this is the smallest subfield containing all three roots. We call this the splitting field of the polynomial x cubed minus 2. We're going to talk more about splitting fields hopefully in the future. And just notice that the splitting field well, let's work out its degree. So let's try to work out the degree of the splitting field in this case. So we can write this. Well, let's write this field as like this. We proved we could do this in previous lecture. So this has degree over cube root 2. So the field that we get by adjoining these two numbers over Q has degree 2 over the field Q adjoin cube root of 2, since square root of minus 3 has a minimal polynomial. X squared x squared plus 3, right, which has no real roots, so it can't have any roots at all, over q adjoin cube root of 2, therefore it's irreducible over that field. So the degree of this field extension is 2, and then the multiplicativity of degrees tells us that the splitting field has degree 6 over Q, because this is the degree of Q cube root 2 adjoin root minus 3 over Q adjoin cube root of 2, which we just proved was 2, times Q cube root of 2, and then for the second of these field extensions, the minimal polynomial is x cubed minus 2, which has degree 3, so this is 2 times 3 equals 6. So in this case, the splitting field or the smallest field containing all the roots of x squared minus x cubed rather minus 2 has degree 6. Okay, that's just something to keep in mind when we talk more about splitting fields. Okay, so, well, what could we hopefully guess from the examples above? So the two examples above suggest that one might expect that the cardinality of the group of automorphisms of K which fix F in a field extension K over F is always less than the degree of the field extension. Because we've seen from these two examples that in both these two examples it's less than, but in the first example we had equality, whereas in the second example it was only a strict inequality. Okay, so you might hope this, and let me just say, you might hope for this, where, let me just say once again, this is the cardinality, or number of elements, cardinality slash i.e. number of elements in the group. Okay, so we're going to prove this, and in fact we're going to prove much more. Let's start with a definition. Let H, so we've, so far we've come up with a construction which will produce a group out of a field extension. We now want to kind of go in the reverse and use a group to produce a field. So let H in ORT K be a subgroup the claim is then that the set of those elements in K which are fixed by all the elements in the group forms a subfield of K. So then the set F, defined to be all those elements in K which are fixed by all the automorphisms in H, so the set of all those elements in K which are fixed by all elements in the subgroup H forms a subfield of K. And then we call this subfield the fixed field of H. Okay, so the proof follows immediately from the definitions. So let A and B be two elements in the set F. Then, for any H in H, we have H of A plus or minus B equals, well, H is a homomorphism, so it's going to be HA plus or minus HB, But H fixes A and B, so it's A plus or minus B, which tells you that A plus or minus B has to also be in F. And likewise, H of AB, since H is an automorphism, is HA times HB equals AB, so that this tells you by definition that AB also lies in F, and likewise for A divided by B. So this is B should be non-zero for this last equation, and that's A over B. Okay, so this tells you that A plus or minus B, A times B, or A divided by B all lie in F, and hence F gives a subfield of K because it's closed under the field operations. Okay, and that completes the proof. And we're almost done with today's lecture, but let me just make one more definition to save me time from next time. So for any field, K, we define K star as the set of all non-zero elements and notice that multiplication makes this set K star into a group because all elements in K star, these are all non-zero elements in the field, are invertible, right? Because we can invert any element other than 0, since all elements of K star are invertible. Okay, so then let's end with one last definition. So a character chi of a group G with values in a field K. So a character chi of a group G with values in a field K is defined to be a group homomorphism from G to K star, considered as a group under multiplication. So it's just a group homomorphism chi from G to K star. Okay, so that's the definition of a character of a group with values in the field, and it turns out to be a rather useful and important notion. Okay, so we'll talk more about characters next time and use this to prove this formula